In this video, it will be helpful if you think of yourself as walking along some of these graphs. So imagine yourself starting at one of the vertices, say, and then trying to get to another vertex. So they even have words like that. They'll describe them called paths that will even sound like you're walking along them. So let me label my vertices. Now, how can you get from A to C? There's more than one way to do it. Obviously, one way to go is just directly AC, or you could instead stop and go A, B, C, or for that matter, you could go A, D, C, and if you wanted to be really tricky, you could go A, B, D, C. And you could even come back to yourself again and get back to A that way if you wanted to. So all of these things that I wrote up here are called paths. Let me write the definition. A path is a collection of adjacent vertices and their edges. Let me go over each of these paths and the way that I'm going to write them. So let's just start with the following path. Very simple. I want to go from A to C in each of these. So I can go A to C directly. So the way I'll draw it, it'll look something like this. If it's really confusing, I might drop to a different color just to make it easier. Another path was A to B, then to C. And if I do decide to have my red, let's see how it looks. It looks pretty good. I like it. So that's how I travel. When you read the book, Mike, who wrote this section or this chapter, he uses arrows for the direction that he's traveling, which that might be easier for some people. For me, I have a difficult time drawing an arrow as I go up there. I'd rather just draw these little scraggly lines. Next, let's try path A, D, C. And so that would look like this, starting at A, then going to D, and then getting to C. Next we'll do path A, B, D, C. Like that. And so it's usually a good idea to make some sort of an indication of the edges as you've walked along and used them, because you can't reuse edges. You can reuse vertices, but not edges. This path, for example, is not permitted, where you'd go to A, go to B, and then somehow come back to A. That's not allowed. Here, usually you'll be given some sort of a picture, like I'm going to do here, and we'll ask you to do and find certain things within them. Here's an example. You can easily find paths in here. Just find 3 paths, nothing special. So you can go as simple as just A to C, just one thing like that. Only paths were necessary. Now here, check this out. You can go B to C back to B, because if you do that, you don't have to use the same edge. You can use a different edge coming back. So that's perfectly fine. But other paths, you can go ahead and play around with these things. Probably B, C, A. Notice that any path that includes A somewhere that's not the beginning has got to end there. Now, of particular interest is a path like the following: B, D, C, back to B. Any kind of a path that begins and starts at the same place has uses you can imagine. Any kind of a delivery scheme where perhaps trucks are leaving from a central distribution facility, being fed all of their packages and then going off in wherever they're going to, but then they have to return. So each of them might have their own path that they follow to get from package 1 to package whatever for the day, but then get back. A path that starts and ends at the same vertex is called a circuit. If I ask you to find a path from A to C in a picture that looks like this, suppose I have A, B, C, D. Can't be done, obviously, because the graph is disconnected. In fact, the defining definition of connectedness, let me write it here. A graph is connected if there is always a path from any one vertex to any other vertex. So if I took the last graph, A, B, I know it's extraordinarily simple, C, D, we could make it connected if I just simply drew an edge to something like that, for example. Any edge, any extra edge that I draw probably is going to make it a connected graph, unless I did something like A to B twice or something like that. But what I have put in there is something called a bridge. A bridge in a graph, I probably should say a bridge in a connected graph, is an edge whose removal yields a disconnected graph. So bridges have unusual importance because they keep everything held together. In the last picture I drew, obviously A to C is a bridge. Even though I think it is really simple, the concept, at least in your head, I'm going to draw a couple of examples nonetheless. In this picture, this simple picture here, AB is a bridge. However, now AB is not a bridge. Now I draw small examples because that's usually what we're going to be doing when we're looking at solving things, is you're going to be looking at sort of an atomic scale, and you're going to be looking at all the parts where they're connected and things like that. What we're looking at here is the graph that started the whole theory of graph theory. Let me tell you where this place is located. It's located in Königsberg, Germany. The name of the man that tried to walk along what are these bridges, his name was Leonhard. And a lot of people think it's Euler, but it's not. It is Euler, one of the most potent mathematicians to have ever lived. Now what we have here is these white lines that you see here. I don't know if you'd call them white lines, but these white things along here are waterways, rivers, if you will. So we have our rivers structured like that. These little bends that you see in the picture, they're bridges. All right, so what Euler tried to do is he tried to start somewhere, and he's physically walking these. He was actually there. He's trying to walk across each of the bridges just one time, but he wants to go across every single bridge to see all the sites. So let me show you some of the difficulties in that. I'm going to choose a color that I hope stands out. I think yellow did that. Let's say we start there. Now, where do we travel from there if we want to try to get through all of the bridges? We might start walking along here and go over this bridge and then come. Now, there's no way back except for one of the two bridges over here. So if I wanted to go over all the bridges, my next thing would be that I have to go through one of these two bridges. So I might do that. Now notice, I don't want to just go back out and go over the other bridge that's right there. I don't want to go back out there because then I will have only used 3 bridges. I'm hardly even done yet. So then maybe we go over this bridge and come over here around like this. And then maybe we try to go here. So I'm back to where I was when I started, but I still have 3 bridges I haven't even gone over. So I could probably do this and then maybe come over this bridge. But then I can't get to that last bridge. I'm stuck. So that's not that surprising of a deal. Let me draw a picture of this situation, but let's mathematicize it, if I can use that phrase. Let me keep the picture up there. What I'm going to do is I can say land masses are like vertices, for example. So I could have an A, I could have a B, I could have a C. We have D, landmass D, and then landmass E. Let me see if I can draw the letters that correspond to them. Landmass E is all the way up there. Landmass A is here. Over here where we started was B. Then I have the letter C over here. And then I have the letter D down here. So there's how I've made my things. So now look at the way that D is connected to A. It's 2 ways. So let me draw that. So I've got that done. Then D is also connected over to B. I got that one. And then I think, what else is A connected to? It's connected to E in there's 2 bridges that lead from A to E. So let me go ahead and draw those. Got it. C. Oh, you know what? Look at this. This is a perfect place to pause. If you'll notice, C, the way I drew my picture is that C in E, that's actually the same landmass. So I didn't even need an E. So let me take it out of there and let me refigure my picture. So I'm going to remove this C. C was really equal to E. So this I'm leaving in the video because that's the kind of stuff you're going to do when you're making up your graphs. If you're lucky enough to have a tablet like I do, you can erase right on the spot. What else do I need to put in? A actually has one bridge going to B. Now, there's also a bridge from C to B. Look at this one. See, I know I wrote C all the way over here, but way over here, this bridge right here connects C and B. So let me draw that. So there's my representation of the situation. Now, to agree with the picture given in the book, I'm going to simply use the picture given in the book. Okay, this is a bit hard to show at once, but you can see the labeling of the letters was a little bit different than mine, but you can see that the basic shape, they don't look much different. Although this line up here is not really there because I got a little piece of the book in when I did it. Now, let me show you why it's so hard to do a path that will take and use up all of the edges. Remember, in this case right now, all of these edges are representing bridges that you can use. So if you try to start from A, look what happens here. I'm going to go from A to B. And then I got to leave B and go one way or another, so I'll do this. So I'm at C. Now, I can go, if I wanted to, I could go and do this. I could go and hit up A. Come back to C like that. And then I could probably come around here. Now where do I go? I can either go to C or B. Now here's where the issue occurs. If you take a look at D, I've got 3 vertices that are coming out of it. If you look at C, I have 5 vertices that are coming out of it. Look at B, I have 3 vertices that are coming out of it, and A has 3 vertices that are coming out of it. Every single vertex in this graph is odd. What happens with an odd vertex is something like this. I'll use A as my example. If you start at an odd vertex, let's say I started at A and it's odd, it had 3 vertices coming out of it. So it had 1, 2, and then 3. Well, if we start at A, you're going to want to leave. But now you have to use all the edges up, so you'll have to come back, and then you'll have to leave. So if you start at A, it has to go to some other vertex. Well, as far as ending. So if I start at A, I have to end at some other vertex and say it's B. That means I didn't start at B. So since I didn't start at B, I'm coming in, like so. I'm going out, like so. But then I'm forced to come back in and be done at B. Now, if A and B were the only 2 odd vertices, I could get from one to the other and probably use up all the edges. But if there's more than that, like in this case, C and D, they're never going to be started or ended with. Another definition. There are a lot of them in this section. An Euler path is a path that uses all of the edges in a graph. And as I've tried to explain, there is no Euler path in the Königsberg bridge problem. Here's another picture of another graph. Let's take a look at, let me read off the degree of each of these vertices. Look at A. There's 1, 2, 3, 4. That vertex has degree 4. Look at B. 1, 2, 3, 4. Look at C. 1, 2, 3, 4. And look at D. 1, 2. All even vertices. Now, watch what happens now. I can go, and starting at A, I can go to B. But then I can come back to A like that, go down to D, then to C, up to B, around C, and back to A. So not only do I have an Euler path, I have what's called an Euler circuit. I was able to start and end where at the same vertex. So we have what's called an Euler circuit. Let me see if I can run over the details again. I'll write down what I did. I started at A, I went to B, so you can kind of follow along in the picture. So I went from A to B, but then I came back to A again. From there, I went down to D, and then C, but then from C I went to B, and then I came back to C, and then I came back to A. So the definition is probably obvious. An Euler circuit is an Euler path that begins and ends at the same vertex. So I've made a couple of graphs to hopefully give you an idea. The degree of the vertices is important in determining what we're going to have. So let me write down Eulers Theorem. And this is for a connected graph. That's important. If every vertex is even, there is at least one Euler circuit. If exactly two vertices are odd, then there is an Euler path, but no Euler circuit. If more than two vertices are odd, there is no Euler path. So forget about a circuit, it doesn't even have a path. Which in the Königsberg bridge problem, that was the issue. We had more than two vertices were odd in that scenario. Here we have a graph, and I'm going to sort of use it to try to describe whether we have an Euler path or a circuit. Now, some graphs you can see pretty easily in this graph here, there's not going to be any Euler circuit. For example, since C is out there all by itself, if I started at C, I would never get back to it. If I started anywhere else, once I got from E into C, it would have to end there. So I would have to end the graph there. But maybe there's a path. Let's count the degrees of the vertices. If you take a look at A, the degree is 2. The degree of B is 2. The degree of E is 3. The degree of D is 2. And the degree of C is 2. So exactly 2 vertices of odd degree. Those vertices, of course, are C and E. So now, the way that you should think of this is because of the little diagrams I drew before, if you start at an odd vertex, you're going to end there, or you're going to end at the other odd vertex. So a good idea, if you want to try to find an Euler path, is to start at one of the odd vertices. So that's what I plan on doing. I'm going to start my vertex at E. So here we started at E, but I'm not going to go directly to C, of course. From E, I can go out to B, and then I can go to A, and then I can go to D, and I can go back to E. And now, since it's an odd degree, it has 1 leaving it, and C has odd degree 1. So let me go ahead and write that out. We started at E, I went to B, then A, D, E, A. And that's the general idea of what you want to do. You want to always start at one of the vertices of odd degree, because that will force you to end up at the other one of odd degree. If you don't do that, there's no guarantee that you're going to be able to get to a path. So make sure you use that as part of your strategy. Let's see what we did. We found the degree of each vertex. That's the first thing you should do. Now, if they were all even, you're going to have an Euler circuit. No problems there. But it's the odd ones that are a problem. The only Euler path when there are exactly 2 vertices of odd degree, according to the theorem. Start at any odd degree vertex for an Euler path. So let me contain a few things in here. So if you're going to have odd degree vertices, if you have more than 2 odd degree vertices, there's no Euler anything. There's no path, circuit, forget about it. If everything has even degree, you can really start at any vertex you want, and you should be able to get back to the same vertex. It may not be easy, but it will be possible. Then the only secondary contingency we might have is if you have exactly 2 vertices of odd degree. In that case, make sure that you start at one of them. Alright, so here's a picture. We're going to try to get an Euler circuit if I can. If not, I'll settle for an Euler path. So let's first of all look at the degree of each of the vertices and see if they're all even. Starting at A, I have 1, 2, 3, 4. Degree of A is 4. The degree of C is 2. The degree of E, 1, 2, 3, 4. The degree of E is 4. The degree of B is 1, 2, 3, 4. That's also 4, and the degree of D is 2. So we have all even vertices. So we have an Euler circuit. So I can start and end at the same place. Well, I'll start at A and see what happens. Starting at A, I can go down to D. And let me just say, I really just picked that at random. I'm really not attempting very much to try to come up with a circuit in my mind. I'm just going where I lead. And I'll avoid the edges I've already used as I go. So I go to B. Now if you can, make as quick work of all the edges that you can like this. You see how I can go right around there. So let me also, while I'm doing that, keep track of what I just did. I did A, then I went to D, then I went to B, I went to A, and then back to B again. Now where can I go from B? Up, and I made, actually, you know what happened? I made a mistake right there. I didn't come back to B. I didn't finish. I made the mistake. There was no vertex where I ended my red drawing. I actually needed to go to E, didn't I? Yes, I did. So let's go ahead and put it here. Now from E, where do we proceed? Well, what I like to do in cases like this, I'm going to use up this loop sort of thing that goes from B and then back to E. So I went B and then E. And then now you can see that this is going to be a cakewalk to finish. I will just then go to C and then back to A. Okay, here is another example, and you can make quick work of this one. Remember, if it has odd vertices, I said to start at one of them. So take a look. I would start at A, because it is an odd vertex of degree 1, but degree B is also 1, so A and B are both odd degrees. So if I were to start at A, I would have to end at B. If I go A, I would have to do all of this business and then finally get to B. I will not get back to A though. However, F, look at it right there. F has degree 1 also. We have more than 2 vertices of odd degree. So what does that mean? No Euler path. And remember, that'll also take out the fact that there's no Euler circuit, because that's an Euler path too. So there's no path, no circuit. This is the floor plan for the Cleveland Museum of Art, at least some of it. Conceivably, when you have a floor plan, you would like people to be able to get in and out of it, probably in a pretty efficient manner. What I want to do is draw a graph to represent this picture, and what I'll do is I'll represent each room according to a vertex. Now, if I'm connecting that room to another one, I will use edges. So for example, take a look here. Going from 224 to 225, there are 2 ways, so I'll just draw 2 of these. And then if I look at 224, these other rooms, I don't know where they go to, but I can't get anywhere else except for those 2 doors. So whatever happens leaving from 224, I'm finished. Now I would like to take a look and see how 225 is related to 231. So we have 1, 2, 3 there. Let me go ahead and put my 231 over here. 1, 2, 3. Hopefully you'll learn as you do these. You don't have to be extraordinarily gifted artistically to draw these graphs. The simpler the graph, the better. You just need all the details of where the edges are and where the vertices are. Now along the side here I have 226. And if I look, it looks like 226 can connect to 225. So there it is going to there. But then the only other place it can go to is a 227. So let me draw that here. I'm going to draw it a little bit to the side because 228 is right next to it. So from 226 I can get to 227, although I cannot get anywhere else. So that takes care of this way out. Now 227 will connect directly to 228. So there's that. But then 228 can go to 225. Got that. Let me make this a bigger dot in the middle. All right, then I have down here 229 and 230. And it looks like 227 goes only to 229. So I'll put that there. And then 229 does connect to 230. So I'll put that there. And then 230 connects to 225. I believe I have everything I want. Now, let's take a look and see if we can actually walk around by using only each door exactly one time. So the first thing we need to do is to check out the degrees of the vertices to see if any of these are going to work. We need to find odd ones. I noticed that 231 is a vertex of odd degrees, so there's 1. 227 is a vertex of odd degree, so there's 2. Now, let me see if there's any other vertices of odd degree. All of these, 226, 224, 229, 230, and 238 are all of degree 2, so there's no problem there. Now let's take a look at this middle one where all the action's going on. I have 1, 2, 3, 4, 5, 6, 7, 8. So I have exactly 2 vertices of odd degree. That means there's an Euler path. But not an Euler circuit. So we have to settle for a path. If you want to settle for a path, it means we have to start at one of the odd vertices. So start at an odd vertex. So remember how this is going to work. If I start at an odd vertex, it is going to end at the other one. So I'm going to start at 231, come back to 231, and go back out to 225. So let me write down what I have so far. I started at 231, then I went out to 225, then I came back to 231, went out to 225, and then I went to 231 a third time, and then I finally got back to 225. So let's make sure that I have all that. That seems like a lot because the way I'm writing this is not the normal way. So we went from 231 to 225, check, then back to 231, check, and then back to 225. Yeah, I figured there is too much of that going on. It might not be a bad idea if I change the letters, but I'm going to try to tough it out and see what happens. So now I'm at 225. What am I going to do? I'm going to take care of this loop around 224. So I'm going to go to 224 and then back to 225. Remember, I'm going to end up at the other odd vertex, which is room 227. So 224 to 225, that's taken care of. Now, I'm ready to take care of these things over here. And you can see it's going to work here. If I go 225 and go around, when I get to 227, I can come in and go to 228, hit 225, and then back and go around and hit 229, 230, back to 227. So let me write down what my steps are there. I'm going to go to 226, to 227, to 229, to 230. I'm actually going different than I said I would. Then I'm going to go to 225. So what I actually did and said are two different things. I went around this way, like so, like that. And then we went 228, and then to 227, like so. And so all we had was an Euler path, but I was able to use up all of the edges.